Janus particles and dual Janus foams, synthesis, characterization, and applications for directional thermal management. Janus particles, JPs, named after the two-faced Roman deity, are asymmetric nano or microparticles possessing two chemically or physically distinct surfaces within a single particle. Their dual functionality enables unique interfacial behavior, controlled self-assembly, and multifunctional material design. Although research on micron-scale JPs has demonstrated promising properties, the scalable synthesis of smaller, less than 500 nanometers, particles remains challenging, limiting large-scale commercialization. Recent seeded polymerization strategies, including emulsion polymerization, have emerged as promising approaches for producing uniform JPs with controlled morphology and functionality. These particles have applications in emulsion stabilization, drug delivery, electronics, and coatings. In parallel, Janus structural concepts have been extended to macroscopic porous materials such as Janus foams and dual Janus foams. These materials exhibit asymmetric wettability, photothermal properties, and thermal rectification, enabling directional heat and mass transport. Such materials are particularly promising for solar desalination, thermal management systems, and energy-efficient buildings. Janus particles, JPs, are a class of engineered nano or microparticles characterized by two distinct chemical compositions or surface functionalities on different hemispheres. The concept derives from the Roman god Janus, who was depicted with two faces looking in opposite directions. This structural asymmetry enables particles to simultaneously perform dual or even opposing functions. Research on JPs has revealed remarkable self-assembly behaviors in bulk phases and at interfaces. These properties arise from their amphiphilicity or heterogeneous surface chemistry, which allows selective interactions with different environments. Despite these advantages, the synthesis of nanoscale JPs, less than 500 nanometers, remains technically challenging to scale for industrial production. As a result, large-scale commercial applications of JPs are still limited. Recently, seeded synthesis methods, particularly seeded emulsion polymerization, have shown significant promise because they are compatible with industrial polymer production techniques. These methods allow controlled formation of JPs with tunable sizes, morphologies, and surface functionalities. The progress in scalable synthesis has stimulated interest in JP-based technologies for applications ranging from emulsion stabilization and drug delivery to electronic devices and advanced coatings. Classification and morphology of Janus particles. Janus particles can generally be classified into three main categories based on their composition: inorganic particles, polymer particles, organic hybrid particles. Their morphology varies widely depending on the synthesis strategy. Typical geometries include spherical particles and anisotropic structures such as dumbbell-shaped particles, acorn-like particles, snowman-like particles, patchy or multi-compartment structures. Among these, snowman-like particles are particularly common in amphiphilic JP systems. For example, amphiphilic JPs can be synthesized through seeded emulsion polymerization, where hydrophobic polystyrene, poly, divinylbenzene, PS, PDVB, domains are combined with hydrophilic silica components. The spatial segregation of these components produces particles with two chemically distinct hemispheres. Synthesis of Janus particles. Seeded emulsion polymerization. Seeded emulsion polymerization is one of the most promising strategies for scalable JP production. In this approach, preformed polymer seed particles serve as nucleation sites for secondary polymerization. By controlling interfacial energies, monomer diffusion, and phase separation, anisotropic growth can be achieved. This method allows control over particle size, surface composition, degree of asymmetry, functionality. The technique is compatible with industrial polymerization processes and enables the production of large quantities of particles. Alternative synthetic methods. Other synthesis strategies include masking techniques, where part of a particle's surface is selectively protected during functionalization. Self-assembly methods, in which phase separation during polymerization produces anisotropic domains. Microfluidic synthesis, enabling precise control over droplet composition and particle morphology. Phase separation polymerization, commonly used for polymer JPs. Each approach provides different levels of control over morphology, chemical composition, and scalability. Characterization of Janus particles. Characterization of JPs is essential for confirming asymmetry and evaluating functional performance. Common analytical techniques include microscopy techniques, scanning electron microscopy, SEM, transmission electron microscopy, TEM, cryo-TEM for soft materials. Atomic force microscopy, AFM, these methods provide structural information and confirm anisotropic particle morphology. Spectroscopic and surface techniques, X-ray photoelectron spectroscopy, XPS, for surface composition. Fourier transform infrared spectroscopy, FTIR, for chemical functionality. Raman spectroscopy for structural characterization. Interfacial and colloidal characterization. Dynamic light scattering, DLS, for particle size distribution. Zeta potential measurements for surface charge. Contact angle measurements to evaluate amphiphilicity. These techniques collectively confirm the dual surface characteristics and functionality of JPs. Applications of Janus particles. Because of their asymmetric structure, JPs possess unique interfacial properties that enable multifunctional applications. Emulsion stabilization. Amphiphilic JPs act as highly effective solid emulsifiers, Pickering emulsifiers, stabilizing oil-water interfaces more efficiently than conventional surfactants. Drug delivery and biomedical applications. Their dual functionality allows simultaneous drug loading, targeting, and imaging. One hemisphere may contain targeting ligands while the other carries therapeutic agents. Electronic and optical materials. JPs are used in conductive inks, sensors, and photonic materials where spatially separated functionalities are advantageous. Advanced coatings. Their anisotropic surface chemistry enables smart coatings with controlled wettability, anti-fouling behavior, and self-healing capabilities. Janus foams, structure and properties. The Janus concept has recently been extended to porous materials such as Janus foams, which exhibit asymmetric surface properties across their thickness. Typically, Janus foams possess 1 superhydrophilic surface, water attracting, 1 hydrophobic or superhydrophobic surface, water repelling. This asymmetric wettability allows directional liquid transport. Water preferentially moves from the hydrophobic side toward the hydrophilic side but cannot flow in the opposite direction. This phenomenon is often described as the water diode effect. Janus foams can be produced through several techniques, including laser surface modification of metal foams, asymmetric coating processes, emulsion templating, directional freeze drying. Such materials are useful for solar desalination, water harvesting, oil-water separation, and cooling technologies. Dual Janus foams and directional thermal management. Concept of dual Janus structures. Dual Janus foams represent an advanced generation of asymmetric porous materials characterized by two independent asymmetries, typically involving asymmetric wettability or chemical composition. Directional thermal transport properties. Unlike conventional foams that are homogeneous, these materials are engineered to perform opposing functions simultaneously, such as heating one side while cooling the other. Recent developments have demonstrated that dual Janus foams can control energy flow and heat transport directionally, enabling applications in thermal energy management. Solar-driven interfacial evaporation. Dual Janus foams have been extensively investigated for solar desalination. In these systems, the hydrophobic top layer absorbs solar radiation and generates localized heat. The hydrophilic inner layer continuously transports water to the heated surface. This architecture provides efficient thermal localization and prevents salt accumulation. As a result, solar evaporation efficiencies exceeding 90% have been reported. Thermal rectification and heat diodes. Directional thermal management is increasingly important for energy harvesting and thermal regulation technologies. Conventional passive heating and cooling strategies typically focus on controlling solar radiation or thermal emission but neglect conductive heat transfer. Dual Janus foams address this limitation by combining photothermal asymmetry with thermal rectification. These materials function as thermal diodes, allowing heat to flow more easily in one direction than the other. Recent studies have reported thermal rectification ratios as high as 122%, demonstrating efficient directional heat transfer. This capability allows selective heat harvesting or dissipation depending on orientation, asymmetric wettability and mass transport. In addition to thermal regulation, dual Janus foams often possess superhydrophilic and superhydrophobic surfaces that enable one-way liquid transport. This property is beneficial for applications such as oil-water separation, fog harvesting, moisture-driven cooling systems. Electromagnetic interference shielding. Certain dual Janus foams, particularly polyamide, pi, composite foams, also exhibit strong electromagnetic interference, EMI, shielding. These materials can achieve shielding efficiencies of approximately 55.8 decibels while maintaining extremely low reflectivity, allowing them to absorb rather than reflect electromagnetic radiation. Fabrication of dual Janus foams. Double-layer emulsion templating. One common fabrication method uses amphiphilic JPs to stabilize asymmetric emulsions. Polymerization of the templated emulsion results in porous foams with spatially separated functional layers. Directional freeze drying. Directional freeze drying can produce aligned porous structures by controlling the ice crystal growth direction during freezing. This technique is widely used to fabricate anisotropic polyamide Janus foams with oriented thermal pathways. Polymer precursors and surface modification. Polyamide precursors. Polyamide foams are widely used because of their high thermal stability and mechanical strength. Their synthesis typically involves aromatic dianhydrides such as BPDA or PMDA, diamines such as ODA. These react in polar solvents like N-methyl-2-pyrrolidone, NMP, to form polyamic acid, PAR. Subsequent thermal or chemical imidization converts PAR into polyamide. Janus asymmetry can be introduced by modifying one surface with silanes or fluorinated compounds. Polycatecholamine surface layers. Polycatecholamines, particularly polydopamine, PDA, are widely used as adhesive interlayers for surface modification. Dopamine hydrochloride undergoes oxidative self-polymerization in alkaline solutions, e.g., tris-HCl buffer, to form PDA coatings. These coatings can create a hydrophilic surface, while the opposite side may be modified with hydrophobic molecules such as perfluorinated thiols alkyl silanes. Polymer matrices and functional additives. Other polymer matrices commonly used in Janus foams include polyurethane, PU, polystyrene, PS, polyvinyl chloride, PVC. Additives may include silica-based Janus nanoparticles as compatibilizers or nucleating agents, lithium chloride, to create hygroscopic regions for moisture-assisted cooling. Engineering applications of dual Janus foams. Personal thermal management. Janus foams can be integrated into reversible textiles capable of providing approximately 9 degrees Celsius cooling in warm conditions and about 11 degrees Celsius heating in cold environments simply by flipping the material. Energy-efficient buildings. Applied to roofs or walls, these materials regulate solar absorption and radiative cooling to improve indoor thermal comfort and reduce energy consumption. Aerospace and electronics. Their lightweight structure, low thermal conductivity, as low as 0.032 WMK, and EMI shielding capability make them suitable for protecting sensitive electronic systems in extreme environments. Conclusions. Janus particles represent an important class of anisotropic materials capable of performing multiple functions simultaneously due to their dual surface chemistry. Advances in seeded polymerization and other scalable synthesis techniques are bringing JP production closer to industrial viability. Beyond individual particles, the Janus design principle has enabled the development of advanced porous materials such as Janus and dual Janus foams. These materials combine asymmetric wettability, photothermal behavior, and thermal rectification to achieve directional transport of heat and fluids. Dual Janus foams, in particular, offer promising solutions for solar desalination, thermal energy management, and advanced engineering applications. Continued progress in synthesis, characterization, and functional design will be essential to fully realize the potential of these materials, as their performance ultimately depends on the integration of both structural asymmetry and application-specific functionality.